Um, so Vladimir is the authority on CP theory, and which is a branch of general topology which deals with spaces of real-valued continuous functions. And it has, he's written numerous articles, and he also has this 4-volume problem book that I'm constantly referring to on CP theory. And CP theory has many applications within and outside topology. My last 3 papers, one has applications to model theory of CP theory, another has applications to descriptive set theory, and another one develops work started by Grothendieck, his famous theorem about closures of countably compact subspaces being compact in function spaces, and showing that various extensions of this are undecidable in set theory. So anyway, it's a very exciting subject for me, and Vladimir will talk today about a particular piece of CP theory, Lindelöf sigma spaces, which seems to have applications. It's raising its ugly or beautiful head everywhere that I turn. So anyway, I'm really pleased that he agreed to talk to us today. Okay, so that's the introduction. Now, hopefully there's some technical person here like David who knows how to, if anything has to be done in terms of setting up the slides or whatever. Okay, are you here, David? Well, it doesn't seem to be here. Ivan, do you know if anything needs to be set up here, or I have no idea how we
I don't think. I only need the permission to share screen. And
yeah, I believe that Shane is the host right now, and she can give her. Yeah, she can, or she can either open the sharing screen or make Vladimir co-host. Yeah,
I'm sharing screen right now. So can you see my screen?
Yes, yes.
Okay. So may I start my talk?
Yes, please.
Okay. So Lindelöf sigma spaces in 2022. And I'm grateful that you received me here. It's an honor to give a talk at this seminar. And yes, I will speak about Lindelöf sigma spaces and their applications, both in general topology and in CP theory. So let me start. From compactness, evidently no need to explain why compactness is important, not only in topology, but in almost all areas of mathematics. And it was introduced in the beginning of the last century as a generalization of closed bounded subsets of R to extend several classical theorems of analysis to metric spaces and then to general topological spaces. However, the space R is not compact, and there are many other non-compact subsets of R that are important in functional analysis and descriptive set theory. The first natural generalizations, such as sigma compactness and local compactness, brought about a plethora of interesting results and theories, but they didn't include the set P of irrationals, which pops up in quite a few applications. That's why analytic sets, that is continuous images of the space P of irrationals, became one of the central notions of descriptive set theory. The peak of the development of the theory of analytic sets was in the early 20th century, when some fundamental papers of Lebesgue, Alexandrov, Hausdorff, Suslin, and Musin were published. And in the second half of the 20th century, specialists in descriptive set theory observed that a natural generalization of the concept is to consider upper semi-continuous compact valued images of the irrationals, giving rise to the class of K analytic spaces. The class of these K analytic spaces is pretty large. And it's not easy to construct a non-analytic subset of R. It takes an effort and a transfinite induction to construct a non-analytic subset of the real line. However, the fact that such sets exist sooner or later had to display a necessity to define a nice class of topological spaces that contain all subsets of the real line, or even better, all subsets of the countable power of the real line, which is equivalent to containing all second countable spaces. So what should we expect from such a class L of sigma? The following requirements seem to be the minimal ones. So requirement 1, every second countable space belongs to L of sigma. 2, every compact space belongs to L of sigma. If a space X belongs to that class F L of sigma, then every continuous image of X belongs to L of sigma. Very natural conditions. If a space X belongs to L of sigma, then every closed subset of X belongs to L of sigma. And finally, every finite product of elements of L of sigma belongs to L of sigma. So these are very natural conditions. If we want the class to be good, then the class better satisfies these conditions. So if we consider the minimal class L of sigma that satisfies the conditions from L1 through L5, then here we are. We have discovered the definition of the class of Lindelöf sigma spaces. So you can see that it appears very natural. If you want some class to contain all second countable spaces, all compact spaces, and have nice, reasonably nice categorical properties, continuous image, invariance under continuous image, under closed subsets and finite products, then there we are. The minimal such class is precisely the class of Lindelöf sigma spaces. But of course, this definition looks more like a list of intentions, and it's not clear how to work with this class and what properties it has. But this class surfaced so many times in functional analysis and descriptive set theory that its spaces were baptized countably K-determined. And it was proved that a space X is countably K-determined if and only if it is an upper semi-continuous compact valued image of a subset of the irrationals, or equivalently, an upper semi-continuous compact valued image of a second countable space. So it's a characterization. Now it's a constructive characterization of the class. If we have these properties, then the space is an upper semi-continuous compact valued image of a second countable space. And these two characterizations of the class of Lindelöf sigma spaces are already useful, intuitive, and can be applied to obtain new information about L of sigma and establish its relationships with other classes of spaces.
But I suspect most people in the seminar do not know what an upper semi-continuous compact.
Okay. Let me give you the definition. Sure, absolutely. If some concept or definition is not known, just interrupt me and ask, please. Okay, so I will stop sharing. Then I will share the whiteboard. And so we have phi from X. It's really not to Y. Let me write it like that, K of Y. Compact subsets of Y. So a map, so compact valued means, So compact valued means phi maps X to K of Y. Now phi is, well, let me write it like that. Upper semi-continuous means that, well, the usual functional notation is applied here, but it means another thing. So phi minus 1 of U is open in X for any U open in Y belongs to the topology of Y. Now, what is phi minus 1 of U? Phi minus 1 of U, it's the set of X in X such that phi of X is not a point, it's a compact set, is contained in U. So this is, it looks like the definition of continuity of a function, but this inverse image means this, that the set of all points whose image is contained in the open set. So this inverse image must be open. And of course, for one single valued maps, this coincides with continuity. And of course, what is in the definition of Lindelöf sigma space, this map must be surjective. So phi of X, again, it's written in the usual way as for functions, but this really means that the union of phi of X, X runs over X, is equal to Y. So I guess now I defined everything about upper semi-continuous maps. Okay, so let me go back. I'll share the screen now. Okay, so these maps, in particular, for example, well, it's more or less evident that just continuous map are upper semi-continuous, and in particular, a continuous image of a second countable space, which is the same as a space with a countable network, actually, but they are all Lindelöf sigma. Okay, and well, one of the manifestations of importance of a topological notion is the number of equivalent definitions for it. So one can easily give 10 or more equivalencies for compactness. But if the concept is of little use, then it's difficult to find two. We will show that the Lindelöf sigma property has at least 10 equivalent definitions. So let us formulate the above observations as a theorem. So the following conditions are equivalent for any space X. A, X belongs to the class L of sigma, which means X is a Lindelöf sigma space. There exists, by the way, there are some chat. I wonder, I can give, oh, it's not for me, because I want, if some chat, appears, I must wonder whether it's a question for me. I guess the best way is just to talk. Anyway, I will check the chat. Okay, so there exists a compact valued upper semi-continuous map, phi from M to X for some M in P, for some subset of the irrationals, such that phi of M is equal to X. So that's one condition. And the second condition is that there exists a compact valued upper semi-continuous map phi from M to X for some second countable space M such that phi of M is equal to X. These are, I already mentioned that, but well, let us formulate it as a theorem. And the topology, so I already said that the analyst came across Lindelöf sigma spaces and they invented, well, not invented, discovered these characterizations of the class. But the topologists came across the class of Lindelöf sigma spaces after Nagami published in 1969 his famous paper about sigma spaces. I won't give the definition of sigma space, there's no need, actually. Although I'll call our spaces this class Lindelöf sigma spaces, but we don't need the definition of sigma spaces. So it is still a classical reference, Nagami's paper. And it soon became evident that the class of sigma spaces with the Lindelöf property, that is the class of Lindelöf sigma spaces, deserves special attention. Since then, Lindelöf sigma spaces occupy an important place in topology. Interestingly, well, I will give 10 equivalent definitions, but I'm not going to give the definition of the class. Historically, topologists discovered this class and used it because they understood that sigma spaces with the Lindelöf property are important. But later, I mean, this origin was forgotten, and there are easier and better characterizations of Lindelöf sigma spaces. So, okay. So, for some time, the same class L of sigma was independently studied under different names in topology, functional analysis, topological algebra, and descriptive set theory. So people in these areas of mathematics discovered this class independently and had their own names for the class. As to the functional analysis and function spaces, in 1979, Gulko proved his classical theorem, which states that if K is compact and Cp of K is Lindelöf sigma, then K is coarse and compact. That is, it can be embedded in a sigma product of real line. Frank, should I define sigma product?
I think you should define, just a minute.
Okay, let me do it.
Can you hear me?
Yes, I can hear you, yes.
Okay, so I would say first define Cp as K, because some theorists may not know that. And definitely also please define sigma product.
Okay, sure. Let me do it right here. So Cp of x is the set of functions, continuous functions, f from x to r, f is continuous. So this is Cp of x. Just the set of all real r, and Cp of x, the topology is taken from the product. It's it's a pointwise convergence topology, but it's taken for the product of x many copies of the real line. So it's evidently contained here in the set of all functions, not necessarily continuous. So and this product has natural Tikhonov topology. So the topology of Cp of x is taken from this product, and Cp of x is dense, by the way, in this product. Okay, so this is the definition of Cp of x, and well, I don't need to go. So let me just define here the sigma product. What is the sigma product of real lines? Sigma, well, let me call it of A. Say A is a set, is the set of points contained in R to A, such that all coordinates of this point, the number of non-zero coordinates or coordinates. So the sigma product, well, usually it can be countable here in the definition, but usually it's always, in practice, it's always uncountable. So it's a subspace of the power of real line, R to A, the functions of real value functions of R, such that the number of non-zero coordinates is countable, of the points of X is countable. So these are the sigma products. And the sigma products are extremely important in functional analysis, in particular, the class of coarse and compact. So K is coarse and compact. If K embeds in some sigma of A, if there exists a set A such that K embeds in sigma of A. Okay, so if there are no more questions, I will clear it. And I will keep, okay, I guess I should clear it again. now, yeah, okay, now I can keep going. Okay, so if K is compact and CP of K is Lindelöf, has the Lindelöf sigma property, then K is coarse and compact, which means it can be embedded in a sigma product of real lines. So this theorem placed the class of these compact spaces whose CP of K is Lindelöf sigma in the middle of the hierarchy of the compactor, which are studied in functional analysis. So these are Eberlein compactor, Talagram compactor, and Corson compactor. Okay, I won't give the definition so far. I guess we won't need them. So Eberlein, let us say, okay, I will say them. I won't write them down. Eberlein compact space is the space whose CP has a dense sigma compact subspace. We could define them like that. Talagram compact space is the space whose CP is K analytic. And Corson compact, well, it's already defined, a subspace of the sigma product of real lines. So this class of compact spaces whose CP is Lindelöf sigma was named Woolcock compact. And because of that, Lindelöf sigma property became a fundamental notion in functional analysis. Okay, so this talk will be structured as follows. We will first present 10 equivalent definitions of the Lindelöf sigma property and establish the basic categorical properties of this class. Then we will talk about numerous applications of the Lindelöf sigma property in topology and topological algebra. And last but not least, we will show how it works in CP theory. So theorem 1, well, that about upper semi-continuous compact valued maps gives two equivalent definitions of the Lindelöf sigma property in terms of upper semi-continuous maps. The following theorem provides two more. It is useful. Is there a question? Okay, seems it wasn't for me. Okay. It is useful if we want to give a short definition of a Lindelöf sigma space. So for any space X, the following conditions are equivalent. X has the Lindelöf sigma property. There exist spaces K and M such that K is compact, M is second countable, and X is a continuous image of a closed subspace of K cross M. So, well, you can see how far away these definitions are from one another. Let me, well, I guess I will draw a little bit here so to illustrate this definition. So we have K, which is compact, M is second countable, we have this product, and we have some closed subset F in the product. So X is Lindelöf sigma if we can map such a set onto X. So we have a compact space, we have a second countable space, and some closed subset of this product can be mapped onto X. This is equivalent again to the Lindelöf sigma property. So, and we can see how far the definitions are from one another. It takes a considerable amount of work to prove the equivalence of the definitions. Anyway, let me erase this. And so what's the next condition? There exist spaces Y and M such that M is second countable, while Y maps perfectly onto M and continuously onto X. And by such spaces Y are called Lindelöf P spaces. That is, X is a Lindelöf sigma space, if and only if it is a continuous image of a Lindelöf P space. Again, I want to draw to illustrate this definition. So I'll go to a whiteboard.
I'm not sure if the set theorists know the definition of perfect map. They ought to, but
Okay, I will give it. Sure, absolutely, no problem, no problem. Please tell me whatever you need to be defined, and I will define it. Okay, perfect map. What is a map? F from X to Y is perfect if, well, by definition, if it has three conditions. One, it's surjective. F of X is equal to Y. Two, the fibers are compact. F minus 1 of Y is compact for any Y in Y. And three, F of X, it's closed. Such maps are called closed. F of X is closed if F in X is closed. So the images of closed subsets of X are closed in Y. The fibers are compact and the map is onto. So this is what a perfect map is. Again, perfect maps are applied a lot in topology. For example, a perfect inverse image of a compact space is compact. There are many. For example, a perfect image of a metrizable space is metrizable. Well, there are many applications of perfect maps in topology. And I wanted to draw a diagram for this Lindelöf sigma property. So X is Lindelöf sigma. So F is Lindelöf sigma. So this is, P is perfect. Here, the weight of M is countable. It's second countable space. And this is just continuous. Continuous or onto map. So X is a Lindelöf sigma space if it is a continuous image of a Lindelöf P space. And P space, P small space, not P capital. It means that we can map Y perfectly onto a second countable space. So I mean here, because of nice properties of perfect maps, a lot of properties, it needn't be second countable at all. For example, because any compact space is Lindelöf P. But it still inherits a lot of nice properties, Lindelöf property, for example, and many others. So I guess I defined all that was needed. Okay. Okay, I will stop sharing the whiteboard and we'll share the screen. Okay, so this is more or less, I tried to give the intuitive notion for this C condition, which is equivalent to the Lindelöf sigma property. Okay, so again, not all definitions of the Lindelöf sigma property are short. This is the shortest one, to say that X is Lindelöf sigma if and only if it is a continuous image of a Lindelöf space. P lower case, because P capital will be another thing. Okay, so let me go ahead. And again, please interrupt me at any moment if you need me to define something. So the following theorem is the most useful one because it gives an internal characterization of the Lindelöf sigma property. We could see that we characterized Lindelöf sigma property in terms of other spaces, continuous image of some other space, a very nice one, but anyway, it was something external. But of course, the Lindelöf sigma property has an internal characterization, and here it is. So for any space X, the following conditions are equivalent. X has the Lindelöf sigma property, and there exists a compact cover. Compact cover means its elements are compact, so all elements of C are compact, such that some countable family N of subsets of X is a network modulo C In which sense? In the sense that for any C, for any element of the cover, and any open subset of X, which contains this set C, there exists an element of the network that gets between them. Actually, it's like a, well, the network in the space it's a generalization of a network in a space, because if you take the compact cover to be the cover of one-point sets, then you'll get the definition of a network. But this is more general. So countable family, its elements could be arbitrary, but the family is countable. And it determines somehow the compact cover, because there is a compact cover of the space such that for any element of the cover and any open set that contains this element, some element of the network gets between them. Okay, and it's the same. There exists a compact cover C of the space X such that some countable family Q of closed subsets of X is a network modulo C. So basically it's the same here, only we say that the elements of our network must be closed. So formally we require a stronger thing, but it's actually equivalent. It's equivalent for, yes, please.
Yeah, so this is just for, there's one cover with this property or any cover with this property? Or any compact cover?
One cover. If you have one cover with this property, then it's a Lindelöf S's space. All covers cannot have this property. It's just impossible. So
okay, thanks.
There exists one cover with this property, then the space is Lindelöf sigma. It's equivalent. And if the space is Lindelöf sigma, then there exists a compact cover C such that the sum countable family is a network modulo C. We could assume them to be closed. Okay, seems that there are no more questions. Okay, so that's the thing. So a space is Lindelöf sigma if it has a compact cover with a network modulo this cover. And now, well, I'll give more equivalent properties for the Lindelöf sigma property to show how it is characterized in terms of compactification. So again, the following conditions are equivalent. The space X has the Lindelöf sigma property. And now let me draw, well, I will read it and then I will draw the situation here. So there exists a compact family F of, there exists a countable family F of compact subsets of beta X, the Stone-Check multiplication of X, such that F separates X from its remainder, from beta X minus X, in the sense that for any X in X and Y in beta X minus X, there exists F in that family of compact subsets such that X is in F and Y is not in F. Let me draw this situation here. So we have, say, X, and it's compact, its Stone-Check compactifications have some additional points, so it's beta X. And so our family F is countable and consists of compact subsets of beta X. So if we have points X here and Y here in the remainder, then some F then some element of that countable family separates, contains the point X and does not contain the point 1. So somehow, well, how could we understand this intuitively? That some countable family of compact subsets separates X from the remainder. So few sets needed to separate the points of these two disjoint sets. Okay, so well, that's how it will be visualized. And let me clear it and keep. Okay, so now here, this separation of X from beta X minus X, is only for this compactification, but actually we could take any compactification. So there exists a compactification Bx of the space X and a countable family K of compact subsets of Bx, which separates X from Bx minus X. So it's we don't need to take beta X to this separation. And actually, we could require even less. There exists a space Y such that X is contained in Y. And for some countable family K of compact subsets of Y, we have, well, X is contained in the union of this family and separates X from Y minus X. So actually the extension doesn't even need to be compact. It doesn't even need to be extension. So X need not be dense in Y. Here, as it's dense in Bx, it's dense in beta X, but it need not be dense in Y. So these are three more conditions equivalent to the Lindelöf sigma property. And seems to be no questions. Let me go ahead. So now the set of equivalent definitions is complete. So it's easy to see that some natural generalizations of compact spaces have the Lindelöf sigma property. So because, well, we saw these equivalent definitions, okay, but where does this class stand with respect to other important classes of topological spaces? So let us note that some important classes of spaces are inside of the class of Lindelöf sigma spaces. So any sigma compact space, or more generally, every K analytic space has the Lindelöf sigma property. What is K analytic? K analytic space is a continuous image of K sigma delta space, and K sigma delta space is the countable intersection of sigma compact space. Okay, so and so in particular, any sigma compact space has the Lindelöf sigma property. And any space with a countable network. Again, if we return to the definition of the network, it's where it is, it's here. So network modular compact cover is this definition. But if the compact cover consists of one-point sets, then it's just called the network. So if a space has a countable network, actually network is as a base, only it's just the definition coincides with the definition of the base, only the elements of the network need not be open in the space. So that's what a network is. So if a space has a countable network, such spaces are often called cosmic actually. So it has the Lindelöf sigma property. Because, well, let me explain it, because just this countable network will be a network modulo the cover, compact cover by singletons. So it's practically evident from one of the characterizations. And, well, another quite big class, any Lindelöf check complete space has the Lindelöf sigma property. Again, it's easy to deduce this from one of the characterizations of the Lindelöf sigma spaces. So if the space is check complete in Lindelöf, it has the Lindelöf sigma property. Well, I guess nobody is asking to define check complete. Let me say a space is check complete if it's a delta subset of its stone check compactification. Okay, so let us show that the Lindelöf sigma spaces form a class with nice categorical properties. So, suppose that P maps X, here exponent, I use exponent for the set of all subsets. So it means the image of every point is a subset of Y. So actually compact subset of Y. So suppose P is upper semi-continuous onto map, and X is a Lindelöf sigma space. Then it turns out that Y is also a Lindelöf sigma space. So that's the first important property. So in particular, if this map is just single value, then we get a continuous image. So in particular, any continuous image of a Lindelöf sigma space is a Lindelöf sigma. I forgot to put is here. Okay. Is a Lindelöf sigma space, and any perfect preimage of a Lindelöf sigma space is a Lindelöf sigma space. Perfect preimage means, what does it mean? It means that if a space Y, say, maps perfectly onto X, then Y, which is Lindelöf sigma, X is Lindelöf sigma, Y maps, there exists a perfect map of Y from Y onto X, then X is then Y is also in a Lindelöf sigma space. And well, any closed subset of a Lindelöf sigma space is a Lindelöf sigma space. And well, the interesting thing here is that you remember that I first gave you a list of intentions of what properties we want the class L of sigma to have. And in this original definition, we only wanted the class to be closed under finite products, but it has even better properties. So if xi is a Lindelöf sigma space for every I in omega, then the product of the spaces xi is also a Lindelöf sigma space. So we we required that the class be invariant under finite products, but we got a class invariant under countable products. So we got a stronger property than we required. And well, if we have an intersection of Lindelöf sigma spaces, then the countable intersection, then the countable intersection of any Lindelöf sigma spaces has the Lindelöf sigma property. And the the countable union, if xi in some space has the Lindelöf sigma property, then the union of xi's I runs over omega also has the Lindelöf sigma property. So countable intersections, countable unions, and countable products, they all preserve the Lindelöf sigma property. And well, again, recalling how we obtained the class of Lindelöf sigma spaces, we obtained them as the minimal nice class, which contains all compact spaces and second countable spaces. So Lindelöf sigma spaces are sort of close to compact spaces in some way. So the natural question is, what properties are left in the class of Lindelöf sigma spaces from compactness? For example, every condensation of a compact space is a homeomorphism. Condensation means it's a Russian term for continuous bijection. So every continuous bijection of a compact space is a homeomorphism. Okay, so, well, I mean, it's in all textbooks. But for Lindelöf sigma spaces, it's false. It's easy to give examples of condensations on a Lindelöf sigma space which are not homeomorphisms. But something is left here. So for this, Arkhangelski introduced the notion of stable spaces or kappa stable spaces. So let me recall that a space X is kappa stable if for any continuous image Y of the space X. So all continuous images of X are good in some sense. In which sense? If I weight of Y is less than or equal to kappa, then network weight of Y is also less than or equal to kappa. What is I weight? I weight is easy. It's the minimum weight of a weaker topology on Y, weaker than the original one. So we take all topologies on Y, well, Tikhonov topologies actually, all Tikhonov topologies on Y, which are weaker than the original one, and the minimum weight of such a topology is called the I weight of Y. So if any continuous image Y of X must be good in the sense that if I weight of y is less than or equal to kappa, then the network weight of y is less than or equal to kappa. Network weight is the minimum cardinality of a network in X. And the space X is called stable if it is kappa stable for any infinite cardinal kappa. And well, since every condensation of a compact space is a homeomorphism, it is evident that every compact space is stable because, well, this could be actually written as the fact that y condenses onto a space of weight kappa, less than or equal to kappa. But if X is compact, then y is also compact, then the condensation is a homeomorphism. And actually the weight of y will be equal to kappa. Well, less than or equal to kappa, and network weight is less than weight, evidently. Okay, so this shows that every compact space is stable. And this notion of stability, I already said, was introduced by Arkhangelsky, but actually this notion was implicitly used by the specialists in functional analysis. And the following result was folkloric before the concept of stability came into official existence. So any Lindelöf sigma space is stable. So that is what is one of the properties left from compactness. Compact space is trivially stable, and it is not trivial at all to prove that any Lindelöf sigma space is stable. So this is a theorem of, again, theorem of Arkhangelsky. And what is the corollary? If the nu of X is a Lindelöf sigma space, then X is omega stable. Nu of X is the Hewitt real compactification of the space X. So that is useful. This fact is very useful in CP theory. And well, let us look at another important property of compact spaces. So
let me interrupt for a second here. This word stable is very interesting. Stability is the one of the most important concepts in model theory, and it's out that the stability in model theory is actually equivalent in some sense to stability in functional analysis. And then when we were working on Lindelöf sigma spaces, something else called stable turns out to be important in the work we were doing applying model theory to Banach spaces. However, I was never able to come up with a good connection between the stability in CP theory and the stability of model theory, and yet both of them seem to be connected to the stability in functional analysis. So I throw out as a problem for the graduate students is somehow to connect all three of these.
It's quite possible that there is a connection.
Sorry?
I mean, this notion is, I guess, more than 40 years old. So it's, I think they should influence one another, stability in other areas. So.
They should, but so far I haven't been able to figure out how. So that's a problem.
Okay. So, well, so any Lindelöf sigma space is stable. Well, compactness is trivial. For Lindelöf sigma space is not so trivial. And if the Hewitt real compactification of a Lindelöf sigma space is Lindelöf sigma, then X is omega stable. Now, let us look at another important property of compact spaces. Any product of compact spaces is compact. Again, this is a classical theorem. And it is stable in particular, compact and stable. But an uncountable product of Lindelöf sigma spaces need not be Lindelöf sigma. It doesn't need to be even normal. So even if you take omega-1 many real lines, for example, you take this omega-1 power of the real line, it's not a normal space. But of course, every real line is a Lindelöf sigma space. So an uncountable product destroys the Lindelöf sigma property. But there is something that is left by the following result of Archangelsk. So any product of Lindelöf sigma spaces is stable. By the way, one might think that the product of stable spaces is stable. This is not true. It is not true even for two spaces. There are counterexamples that a product of two stable spaces could fail to be stable. But if you have stronger property of Lindelöf sigma, then any product of Lindelöf sigma spaces is stable. So that is another thing that is left from compactness. And G delta diagonal, what is G delta diagonal? Well, it means precisely that the diagonal in the square is a G delta set. G delta set is the intersection of countably many open sets. So G delta diagonal over space X, well, it's important because of a well-known theorem of Haber, that any countable compact space with a G delta diagonal is second countable, hence metrizable and compact. So G delta diagonal, say in compact spaces. This is not trivial. Haber's theorem is for countable compact spaces, but it's not trivial even for compact spaces, that a compact space with a G delta diagonal is metrizable. And by the way, for pseudo-compact spaces, this is already false. A pseudo-compact space with the G delta diagonal could be very big. Okay, anyway, it turns out that there is an analogous fact for Lindelöf sigma spaces. So if a Lindelöf sigma space X has a G delta diagonal, then X has a countable network. So again, it must be small. So if a Lindelöf sigma space has a small diagonal, it must have a countable network. If we omit sigma property here, just take Lindelöf space with a G delta diagonal. It's also small. It condenses, so that it has a continuous bijection onto a second countable space, but it needn't have a countable network. But a Lindelöf space X, Lindelöf sigma space X with a G delta diagonal must have a countable network. And Theorem 3, what is Theorem 3? Well, I won't go to it, I'll just repeat it. Theorem 3 says that a space is Lindelöf sigma if and only if it has a compact cover for which there exists a countable network. Okay, so this compact cover evidently determines quite a few properties of the space X. So the following theorem is an illustration of that. So if X is a Lindelöf sigma space and every compact subset of X is finite, then X is countable. There are many spaces in which compact subsets are finite, but if they could be pretty big, what discrete space. But if X is Lindelöf sigma and every compact subset of X is finite, then X must be countable. And we will next present two very non-trivial results about Lindelöf sigma spaces. One of them is the theorem of Portal. And he proved his theorem after Archangelsk established that every hereditary Lindelöf P space is second countable. So let me recall that Lindelöf P space, P lowercase, means the space maps perfectly onto a second countable space. So it needn't be second countable, but if every subspace of X is Lindelöf P, then the space has a countable base. This is a theorem of Archangelsk. Now, Hodel proved the analogous theorem for Lindelöf sigma property. So a space X is cosmic means has a countable network, if and only if every subspace of X has the Lindelöf sigma property. So hereditary Lindelöf sigma property implies that X has a countable network. And this theorem is highly non-trivial. It requires a lot of work for its proof. But anyway, it's the theorem of Hodel. And well, it's a famous result of Mishchenko. obtained in maybe 60 years ago, more or less, that every countable compact space with a point countable base is metrizable. However, Shakhmatov proved that pseudo-compact spaces with a point countable base can be arbitrarily big. Besides, in some modules of ZFC, even a hereditary Lindelöf space with a point countable base need not be metrizable. But the following result shows that this cannot be stated about Lindelöf sigma spaces, and it's a consequence of a theorem of Haber. So if a Lindelöf sigma space X has a point countable base, then X is second countable. So point countable base in Lindelöf. It's let us say, Grunheig proved a much more general theorem. It's a consequence of a general Grunheig theorem that a Lindelöf sigma space with a point countable base must be second countable. And point countable means every point belongs to countable many elements of that base. In general, a space with a point countable base need not be second countable. Metrizable space has, any metrizable space has a sigma discrete base, which is point countable evidently. So usually you don't have second countability from point countable base, but if you have a Lindelöf sigma property, then yes, you have countable base in such a space. And now let us look at some examples, classical examples of Lindelöf sigma space and spaces which are not Lindelöf sigma. So if we take the Sorgenfrei line, okay, if anyone needs me to define it, I will, but no need, okay. So the Sorgenfrei line is an example of a hereditary Lindelöf space, which is not Lindelöf sigma. So it could be hereditary Lindelöf, but it's not Lindelöf sigma. The Sorgenfrei line. And if we take one point Lindelöfication L of an uncountable discrete space, then it is a Lindelöf space with a unique non-isolated point, which is not Lindelöf sigma. So what is Lindelöfication? Well, you take, well, let me draw this to illustrate. So you take a big discrete set, you take a point, say P, and this is L. So what is Lindelöfication of this discrete space? The basic neighborhoods of, well, neighborhoods of P are complements of countable set. So U belongs to tau P L if and only if L minus U is countable. So this is what one point Lindelöfication, it's like one point compactification, but for a discrete space in compactification, we take the neighborhoods of this point to be the complements of finite sets. But if we take the complements of countable sets to be the neighborhoods of the point P, then that's Lindelöfication. Okay, so this one point Lindelöfication has only one non-isolated point. It is a Lindelöf, but it's not Lindelöf space, but it's not Lindelöf. And another result is the classical theorem of Shapirovsky. He proved that if the tightness of a compact space is kappa, then X has a pi base of order at most kappa. Okay, let me decide. Tightness less than or equal to kappa. Well, I will draw here. By definition, this means for any A in X, if X belongs to the closure of A, then there exists B, subset of A of cardinality at most kappa, such that X belongs to the closure of B. So it's X, A sort of touches X, the point X, then there is a smallest set B, smallest set B of smallest of cardinality less than or equal to kappa, which touches the point. This is what tightness less than or equal to kappa means. What is pi base? Okay, a family B of non-empty open subsets of X, star means non-empty open subsets of X, is a pi base of X if, well, for any non-empty open subset of X, there exists B in B, such that B is contained in U. So it looks like a base, only it does need to contain a given point. So a family of non-empty open subsets of a space is a pi base if those elements get into any non-empty open set. And pi, yeah, so I guess I defined all here. And order, what is order? Order kappa means any element belongs to at most kappa elements of the pi base. So point countable base, you saw already that has very strong consequences. A compact space with a point countable base is metrizable. A Lindelöf sigma space, a Lindelöf sigma space with a point countable base has a countable network. But if we only consider pi base, then small order doesn't imply such strong things. For example, in compact spaces, if tightness is at most kappa, then there is a pi base of order kappa. Again, it's a highly non-trivial theorem of Shapirovsky. And this result cannot be directly extended to Lindelöf sigma spaces, because even countable spaces, for example, if we take the omega-1 power of the real line, it's separable. So we take that countable space, it doesn't have a point countable pi base. But I proved that the following facts, well, extended this theorem of Shapirovsky in some way. So if you have an infinite cardinal kappa, and X is a Lindelöf sigma space whose tightness is less than or equal to kappa, and pi character. Pi character means a pi base at the point less than or equal to kappa, means you have kappa many non-empty open subsets such that every neighborhood of the point contains one of them. So if you have tightness less than or equal to kappa and pi character less than or equal to kappa, then it has a pi base of order kappa. So for tightness, just tightness, for compact space, actually tightness in compact spaces implies pi character at most kappa. So in compact spaces, you only assume tightness, but you have pi character automatically, which is false for general spaces. But for Lindelöf sigma spaces, it is false, for example. But if you have tightness, small tightness and small pi character in the Lindelöf sigma space, then the space has a pi base of order less than or equal to kappa. In particular, these two properties are weaker than character. Character is a minimum of a cardinality of a local base as a point. So if the character is at most kappa, and X is a Lindelöf sigma space with that character, first countable, for example. If X is a first countable Lindelöf sigma space, then it has a point countable pi base. In general, pi base of order at most kappa. And another consequences of Lindelöf sigma property have to do with dyadic compact spaces. So dyadic compact space, a compact space is dyadic if it's a continuous image of a counter cube. So Yesenin-Volpin proved long ago in the last century that first countable dyadic spaces are metrizing. Arkhangelsky strengthened this result, proving that any dyadic space of countable tightness is metrizing. But dyadic compact space is a continuous image of this counter cube. D is 0, 1, what set theory is just denoted by 2. I don't like to denote it by 2 because 2 I use it for other purposes. It's just the doubleton, 0, 1. D transparent is what set theorists usually denote by 2. D to the kappa for some cardinal kappa, then Tkachuk generalized Arkhangelsky theorem about metrizability of dyadic spaces. So if we recall that the counter cube is a topological group, trivial. So if G is a Lindelöf sigma group, that is a topological group whose topology has the Lindelöf sigma property, then the weight of K is equal to the tightness of K for any compact continuous image K of the group G. So you see here the group is very specific, it's the counter cube. But if you take any Lindelöf sigma group and you take any compact continuous image of this Lindelöf sigma group, then its weight is equal to its tightness. Means if tightness is countable, the compact is metrizable, the compact space is metrizable. So for example, if K is a compact space of, as a consequence, compact space of countable tightness, and K is a continuous image of a Lindelöf sigma group, then K is metrizable. It's again a very, very strong theorem of Tkachuk, and a very difficult. I guess the complete proof takes about 15 pages. Anyway, and in topological groups, I'm already passing smoothly to CP theory because it's topological algebra. So I'll talk a little bit about applications of Lindelöf sigma property in topological algebra. So it's important to know when a given group has the Suslin property. Suslin property means any family of non-empty, any disjoint family of non-empty open sets is countable. And for example, we have this inequality, I weight of G is less than or equal to Suslin number of G by pseudo character of G for an arbitrary group G. Pseudo character means the least number of open sets such that any point is the intersection of, well, not any point, a given point is the intersection of this family. Now, if G, the topological group, is compact, then it has the harm measure. There is a harm measure on G, and this easily implies that G has the Suslin property. And actually, the methods of measure theory make it possible to prove the same result for every locally compact sigma compact topological group. But Tkachuk proved that local compactness can be omitted in the above results and proved this important theorem that is, if G is a sigma pseudo-compact topological group, then G has the Suslin property. In particular, if G is sigma compact, no need of local compactness here, then G has the Suslin property. And Uspensky strengthened Tkachuk's theorem, proving the same theorem for Lindelöf sigma groups. So any Lindelöf sigma group must have the Suslin property. For example, if we look at CP of X, it's dense subspace of the power of the real line. And the power of the real line has the Suslin property because of Hewitt-Marchevsky condition. Anyway, as we mentioned above, the main line of research in the theory of Lindelöf sigma spaces is to find out what properties of compact spaces also hold for Lindelöf sigma spaces. So let us look at more of that. So let us look at the following property of compact spaces. If X is a compact space and F maps X onto Y, continues on to map, then for every separable closed set F in Y, we can find a countable set A in X such that F of the closure of A is F. It's a trivial property because A is dense, F of A is dense in F, the image is compact, so it has to coincide. So it's for compact spaces, it's trivial. But if we only assume that X is Lindelöf sigma, then it is not clear at all why this property should hold even for second countable spaces. But it turns out that there is a version of that property for Lindelöf sigma spaces. And it was a main tool in proving a result in CP theory. So let us assume that X is a Lindelöf sigma space and F maps X onto Y is a continuous onto map. So if hereditary density of y is less than or equal to k, then there is a set A in X such that the cardinality of A is less than or equal to kappa, and f of the closure is y. So something like that property of compact spaces, but for the whole space, and we must assume hereditary density to be small to have this property. But even this corollary is not, this corollary shows that some spaces cannot be continuous images of Lindelöf sigma spaces. So if a Lindelöf sigma space is kappa monolithic, what does it mean? The closure of any set of cardinality kappa has network weight at most kappa. So if y is a continuous image of X and its hereditary density is at most kappa, then its network weight is less than or equal to kappa. It sounds technical, but it implies, for example, that if you take the two arrows space or the Tikhonov cube, X equals to Tikhonov cube for some uncountable power of, or you take X equals beta omega, then X is not a continuous image of an omega monolithic Lindelöf sigma space. Well, it's not so easy to prove that some space is not continuous image of something. Anyway, now before I pass to CP theory, let me recall that a space is functionally countable if the image of X is countable for any continuous function f from X to R. And these spaces were first studied by Walter Rudin in 1957. So it's an important class which has been around for more than 60 years. And it's known that ordinal sigma products, what is sigma product? Sigma product means only finitely many coordinates are distinct from coordinates of a given point. So sigma products of Cantor cubes and Lindelöf P spaces, what is P capital space, is a space in which G delta subsets are open. So Lindelöf P spaces are functionally countable. Lindelöf scattered spaces are functionally countable. A space is scattered if any non-empty subspace of this space has an isolated point. So, and a compact space is functionally countable if and only if it is scattered. So in particular, any finite product of functionally countable compact spaces is functionally countable. But there was a question about product of two functionally countable arbitrary spaces, and it was proved in 1985. It's Hernandez, a guy from Spain, who proved it. Actually, what is the example? You take 1 point Lindelöfication of the set of cardinality omega 1, discrete set, and omega 1. They are both functionally countable, but their product is not functionally countable. Anyway, one of these spaces is countable compact, and the other one is Lindelöf. But for example, functionally countable compact spaces are scattered, but sigma compact functionally countable spaces need not be scattered. So it's not clear whether the product of two Lindelöf functionally countable spaces is functionally countable. So I proved recently that the following fact is true, that if you have finitely many functionally countable spaces and their product is Lindelöf, then X is functionally countable. So if the product is Lindelöf, then we preserve functional countability in product. In general, we do not. In particular, if Xi is a functional countable Lindelöf sigma space, this was a new result for Lindelöf sigma spaces also. Then their product is functionally countable. And now let me formulate you some very recent results about Lindelöf sigma spaces. So maybe I will, because I have little time, maybe I will skip that and pass to CP theory. Let me skip this. Yeah, okay, I think. So I will talk about this topological property of general Lindelöf sigma spaces, which came from CP theory. So it's Actually, this is a transitional segment from general topology to CP theory. So well, 5 years ago, me and my student, PhD student Guerrero Sanchez, we discovered an interesting property of a sigma product of the counter cube. So S is the set of points in the counter cube, 0, 1 to omega 1, such that the number of non-zero coordinates is finite, sigma small product. So what is the property? The property is what we call discrete selectivity. So if you take any sequence of UN of non-empty open subsets of that sigma product, then you can pick a point xn in UN in such a way that the selection is closed and discrete. Maybe many of you know that there is a very strong school of topologists who study selection properties of topological spaces. It's led basically by Marion Skippers, but many other topologists contributed to that. Hague in particular, many other famous topologists contributed to selection, to the study of selection properties. So it's a selection property too. We have non-empty open subsets. We can select a point from every set in such a way that the resulting set is closed and discrete in that sigma product. So that's the property this sigma product had. And so it turned out to be important in many other contexts. So I formally introduced it and studied it in the next year, in 2018. So let us call a space discretely selective if for any sequence, well, the same, UN of non-empty open subsets of X, there exists a closed discrete set D, Xn, and omega such that Xn belongs to UN for each n and omega. And the set D will be called a selection for the family D. Okay, now, what does this discrete selectivity say about a space? It says that X has many closed discrete subsets. For example, a discrete space is discretely selective, evidently. But discrete selectivity, CP, the space is CP of X, they are not discrete at all. But it turns out that almost all spaces CP of X have this property. So, well, a space X is uncountable if and only if CP of X is discretely selective. So we have discrete selectivity in all non-metrizable spaces CP of X, because for countable spaces, it's metrizable. Metrizable spaces don't have discrete selectivity. So almost in all spaces CP of X, we have this discrete selectivity. But if we look, transparent is just 0, 1, the segment 0, 1. But this space is even compact for a discrete space X. And by the way, in trivial observation, compact spaces do not have discrete selectivity, evidently, because we don't have infinite closed discrete subsets there. So, this theorem doesn't hold for the spaces CP of Xi. So it's a very interesting question to find out when CP from X to I is discretely selective. So, and well, evidently we must introduce some property of X that implies discrete selectivity of CP of X. So I introduced in the same paper this property. So given a space X, let us call A in X inessential if there exist countable disjoint subsets B and C of X minus outside of A. So they are disjoint, but their closures intersect. And the space X is essentially uncountable if any countable subset of X is inessential in this sense. So this notion is stronger than uncountability. It formalizes an intuitive idea that no countable subset of X contains all non-trivial information about countable sets. So for any countable set, outside of it, we have something non-trivial, two disjoint countable sets whose closures intersect. So that's the intuitive significance of essential uncountability. And it actually, one of the results I proved about this, that any Lindelöf sigma space is essentially uncountable. And in particular, CP of xy is discretely selective. And by the way, this result is not trivial even for compact spaces. It's not so evident why any compact space is essentially uncountable, of course. Uncountable compact space is essentially uncountable. But it turns out that it's true even for Lindelöf sigma spaces, and for all Lindelöf sigma spaces, its function spaces in the unit interval is discretely selective. Well, I already talked about that theorem of Bulko, so let me formulate it as a theorem. So if X is a compact space and CP of X has the Lindelöf sigma property, then X is coarse and compact. That was the famous result of Bulko. And it's difficult. It was very difficult to prove, extremely difficult. The proof Bulko wrote was for 20 pages, more or less. Recently, we discovered a shorter proof, but well, let me not talk about this. But well, I generalized that Bulko theorem omitting compactness of the space X. So I proved that if you have any Tikhonov space and CP of X is Lindelöf sigma, then X condenses into a sigma product of real lines. Condenses means there exists a continuous injective map. So if X is compact, this condensation is a homeomorphism, so it's coarsened because it embeds in the sigma product of the real lines. So this is a generalization of Bulko's theorem, basically from compact spaces to any space. So that's what I proved. And if both X and CP of X are Lindelöf sigma, then CP of X linearly condenses into a sigma CP of, well, here X condenses always. But if both of them are Lindelöf sigma spaces, then CP of X linearly condenses, the space CP of X linearly condenses into a sigma product of real lines. And well, I already talked that these are generalization of theorem of Bulko. So, and it's natural to call a space Bulko space if CP of X is Lindelöf sigma. Because for compact spaces, a compact space is Bulko compact if its CP is Lindelöf sigma. So in general, we could call a space Bulko space if its CP is Lindelöf sigma. And if we want to study Lindelöf sigma property and its implications in function spaces, then there are two main questions to look at. What happens if CP of X, in CP of X, if X is Lindelöf sigma space? And what happens in X if CP of X is a Lindelöf sigma space? So there are two main lines of research. For example, any Lindelöf sigma space is stable by one of the theorems we saw today. Arkhangelsky established that stability of any space X is equivalent to monolicity of CP of X. Monolicity means the closure of any set has the network weight, because the whose cardinality is equal to the cardinality of the set. So this gives the first important information in the direction of the first question. So if X is a Lindelöf sigma space, then CP of X is monolithic. Means the network weight of the closure of A is at most cardinality of A for any subset in CP of X. In particular, if CP of X is separable, then both X and CP of X have countable network. So if X is Lindelöf sigma space and CP of X is separable, then both spaces are small. They have countable network. And well, I guess I will finish soon, but I have to mention this fundamental result of Baturov. It was proved in 1987, and it still brings very important applications. So if X is a Lindelöf sigma space, then for any subset Y in CP of X, the Lindelöf number of Y is equal to the extent of Y. Well, extent means the supremum of closed discrete subspaces. Lindelöf number means the minimum cardinality of subcover for any cover. Okay, and well, so I guess to leave some space for questions, I will stop here, and let me go to the last page. No, I won't. I stop here. I will tell you that you could find more information and a great deal of open problems in the following survey papers. So my papers, Lindelöf sigma space is in the present class. It published in 2010, but some of the open problems they are solved, but the majority of them are still open. And a more recent survey on CP theory, 16 years of CP theory, questions of answers, published in 2017. And if one wants to work with CP theory, then these are my 4 books, which introduce to all popular topics of CP theory. The first volume published in 2011, the second one in 2014, and so on. The last volume published in 2016. And I guess now that's the last page.
Well, thank you very much. You have inundated us with lots of material. I have several questions and comments, but let me ask first if other people in the audience have questions or comments.
Hi. Yeah, so a quick question. I think like halfway through the talk, you mentioned this result about G delta diagonals with so sigma Lindelöf spaces with G delta diagonals have a countable network. So I was wondering if it's known that that is sharp, or if there is some hope to get like a little better from that.
This inequality is sharp. This I didn't quite understood the question, I'm afraid. Yes, if a Lindelöf sigma space has a G delta diagonal, then yes, it has a countable network. It needn't have a countable base. For compact spaces, a compact space has a countable base, but Lindelöf sigma space doesn't need to have a countable base. It only has a countable network, which is the same as base, but its elements are not countable. So I wonder whether I answered your question.
Yes. So Ivan, it wasn't quite clear what you meant by saying it was sharp.
Yeah, I didn't quite get that. I mean,
yeah. So yeah, with sharp, I was thinking exactly that. Like, if there are examples of sigma Lindelöf spaces that are not second countable with that G delta diagonal.
Yes, there are such examples. If you take, for example, counter cube of weight omega 1, okay, and you take a dense countable subset, it's separable, it's known. So you take a dense countable subset, then this dense countable subset, well, it's countable. So sigma compact is Lindelöf sigma. And because of countable, its diagonal is G delta, it's much stronger, but it doesn't have countable base. So that's the example. So in this sense, yes, the inequality is sharp.
Okay.
Yeah. Thanks.
Go ahead. No. Other question?
No, that was my question.
Okay. All right, let me make a couple of comments. Some people in the seminar study C-star algebras, and C-star algebras are related to Corzen compacta. And so maybe there's some application of Lindelöf sigma spaces to C-star algebras. I don't know. People in the seminar certainly know about Rothberger spaces and Borel's conjecture, and the functionally countable that he was talking about. If I remember correctly, saying that Rothberger spaces are functionally countable is equivalent to Borel's conjecture.
Yes. Actually, Frank, he recently, well, it's not CP theory. I work also with Richard Wilson, you know him, I guess.
Yes.
And he mostly works with, not mostly, but works a lot with linearly ordered spaces and generally ordered spaces. And we obtained some results for generally ordered spaces. There is a theorem we obtained, which is equivalent to a weaker form of Borel's hypothesis. Maybe your people would be interested in that. If you are, we could send you a preprint.
Another comment, it seems that spaces with a dense Lindelöf sigma space are also very interesting. I have been reading this book, I don't know if you're familiar with it, by Tkachuk, Kubish, and Lopez Pellice, Descriptive Topology in Selected Topics of Functional Analysis. And there they prove a bunch of things about web compact spaces, and they have, that's equivalent to having a dense Lindelöf sigma subspace. And I think there's some set theory they haven't looked at with these web compact spaces, because it involves partial orders included in omega into omega.
Yeah,
and there are so many set theoretically undecidable things about omega into omega. And I'm feeling that if somebody looked at this from the set theoretic point of view, they'd be able to prove something there. So that's something, again, for the graduate students to do. Let's see. Yeah, those were my comments. And I'm certainly going to ask you to give me a link to your slides, because there's lots of.
I will just send it to you by email. There is no link to that slide, but I will just send you the PDF. It's a PDF file. I will send it to you by email.
Good. And then if anybody wants that, they can ask me to resend it to them. All right, Yvonne, you'll also get it. Okay, do we have other questions?
I have one question. David, do you hear me? Are you here?
Yes, I hear you.
David, so could you then send me, I already gave my talk, so could you send me the letter we talked about?
Yes. I have arranged that there will be a letter.
Thank you.
Okay. Do we have other questions? Yeah, I'm still resisting giving talks this way, but when we get back to in-person talks at the seminar, I will give other applications of Lindelöf sigma spaces in a variety of places in general topology and set theory. Hopefully that'll be in September. Okay, if there are no other questions.
I will wait the last remark. Because you, it's a hurting point for us that we cannot give the talk in person, that we must give talks like that, and it takes more time to prepare because everything must be electronic and all that stuff. But I just wanted to comment that here we have Vera Fischer, and I am Vera. Do you hear me?
Yes, I hear you.
Okay, so I am proud to say that recently, well, not so recently, in October, I gave a personal and in-person talk at the seminar of Vera Fischer in Austria. Yeah, so this happens sometimes in spite of pandemic, but well, I am proud to say that I at Kurt Gödel Research Center, so it was in October that I gave an in-person talk.
Good.
Yeah, it was great having you. Yes.
Will you be going to Vienna or Prague this summer?
Well, it's difficult. You see, I didn't have American visa because of pandemic. My visa expired in 2020. I had to wait before I could get the new visa to renovate the visa in 3 months. Now I waited for 1.5 years and all deadlines passed. I couldn't, so I guess I won't go.
Oh, that's too bad. Anyway, Okay, well, Vera, I hope to see you in July in Vienna.
Oh,
And,
so you're coming? That's great. Fantastic.
I haven't yet booked the flight, so I'm not promising, but
Okay.
trying to.
All right. Okay. Well, I'll send you an email if you want to stay a little bit longer or something. Okay, great. Perfect.
Okay, I'll be talking to you. All right, any other comments or questions before we close? If not, I again thank Vladimir for this very interesting talk, and there's lots of research that's going to come out of it. Thank you.
Thank you.